All right, so quickly, there was something I did not mention on Q versus K yesterday, and it was that we always have to respect that, like, eventually if Q is different than K, it wants to equal K, so the reaction will proceed until...
Good morning, teachers, for planning, first period planning. The PDs are in the media center at 7:20. All teachers with first period planning. The PDs begin at 7:20 in the media center.
Okay, so eventually Q will become K. So we want to say that the Q will approach K, even if it's going in the reverse reaction or the forward reaction. We always like to say Q approaches K. So that's the terminology that you might want to be familiar with, because you know, like we have some terms that we should be stating, like in kinetics, we have to like say the molecularity of the rate determining step, or sorry, the slow step equals the rate law orders. Like there's some phrases you should be very familiar with to make sure that you're saying things that you want to say concisely, so you're not wasting like paragraphs of information. Okay, so the graph or the chart here is kind of one of the ones you saw yesterday in your little animation. So if Q is less than K, do I have too many products or too many reactants? Too many reactants, because Q is products of reactants. How do I make a numerical value small? Is the numerator bigger or is the denominator bigger? The denominator is bigger. That means that's going to drive the number down. So we want to make more products and decrease the reactants to make Q equal K. And the opposite of that, when Q is too high, who do you have too many of? Products. So that number is too high, so you want to get it to go down. And by nature of how that's going to work out, the reactants are going to go up, so it's going to make the value get smaller. So that would be proceeding which way? Proceeding left. Good. Proceeding towards the reactants. Okay. So I have to flip around because I did some questions yesterday that jumped ahead. Today's, yeah.
So I know that like K is like the equilibrium constant, but what is that like actually?
K is the ratio of reactants to products at equilibrium. Okay. Question?
Is K, all that the same thing as
KEQ is a cheap way of just saying, I don't know which one I'm talking about. It's just the K equilibrium constant. But many times, like if I'm saying solve for KEQ, it's because you're going to use the data that's given to you, and you'll just solve for the K. But if they give you values like atmospheres, you're going to be solving for KP. If they give you values like concentration, you're essentially just solving for KC. So KEQ is just a cheap way of saying I'm K, but it's not a specific one. Because eventually, not tomorrow, but the next day, no, next week, we'll be talking about KSP, which is K of solubility product, and it's a very specific type of question. So sometimes the little subscript gives you information about the style of question you're dealing with. Okay, so go right now, figure out if this reaction, so here's the reaction, here's your K, given this initial information, what's going to happen? Take a minute, make sure you put your guys calculate for me. You guys know what you're doing? No response. Using those concentrations, and what are you plugging in to find? Your what? So when I plug these values in, I'm essentially solving for what? Q. There you go. We're solving for Q. Because it says these are the like initial conditions, so given the following conditions. And wait, the way you know you're solving for Q specifically is if you're given a concentration or a number for each reactant and product. So you're not starting with zero of anything, so you have all non-zero numbers. So this is in 14.5 liters. So we don't just plug the numbers in, we have to find what? Molarity first. So Q is set up the same as K. So it's whatever what? So nitrogen monoxide squared times oxygen over nitrogen dioxide squared. So we're going to plug these values in here. So I'm just going to scroll up a little bit for myself. So you guys got calculators, be my human calculators. What is the concentration of nitrogen monoxide? Oh, actually, this one does not give you sorry, this one does not give you nitrogen monoxide. I was looking down here. So does it, noticing that it does not give you nitrogen monoxide, what should you already know? Well, given the fact that it's not giving you an initial concentration, you're going to say that is 0. So, sorry, I'm trying to pull this reaction back up. Is nitrogen monoxide a product or a reactant? Okay, so which way does this have to proceed? Towards the products, because there are none of them, right? So if you can't take away something you don't have. So if you have 0 of this, you have a number here and a number here, there's no question which way this one has to proceed. Because you don't have any products, you need to go ahead and make products. So you're going to subtract reactants and add products at a certain ratio. So we actually already know which way this one will proceed. There was no comparison between Q and K simply because of the omission of one of the products. For the next one, we're given nitrogen dioxide, monoxide, and oxygen in a 10-liter container. Now, determine which way this will proceed. So you're my human calculators. What am I plugging in? So Q equals, what's this one? Say that again? So nitrogen monoxide, so 0.40 divided
Please
by
stop interruption.
10 liters.
Please set your recycling bins outside your classroom. Thank you.
I don't have any. So what's that concentration, guys? 0.04, because it's just dividing by 10, squared, because that's squared. And then what's oxygen's concentration? Okay, so it's the same, just a decimal less. And then divided by 0.2, right? And that is squared. So what's that value? Make sure you're putting like double parentheses to hold your numerator together as one. I heard somebody start with me. What is it? 4 times 10 to the -4. Is that value greater or less than K? Way less, right? Okay, so what's the problem? Do I have too many reactants or too many products? Too many reactants. So Q is less than K, which is 0.5, I think it said. So if you have too many reactants, which way do you need to proceed? Towards the products, right? So this will proceed right until Q equals K. So that means equilibrium has been achieved. All right, so I have some confused faces. Give me a thumbs up if you're feeling okay with comparison of Q and K. And do you know, like, do you feel good, like, if you see that you have all the or all numbers given to you for every reactant product, does that trigger you to find Q? Okay, because you have to find Q because you will not know which way to proceed, like subtracting from reactants to products. Yeah. Once you got there, we didn't solve for it yet. So let me go ahead and let's jump to homework then, okay? So I have some more problems I would like to do with you, but if I clear up homework, then we maybe won't have to do all those. Where did I put this? Okay, so I have some of them here, and then others I have on my PDF. I'll pull up in a second. So I'm just going to go one by one, and then if I'm going too fast, slow me down. Okay. So in the first set, it asks for you to find the equilibrium. No, find the equilibrium concentration. Yeah. Okay. So it already established equilibrium. You gave your K value. You set up your K expression. Thumbs up. Yes. Okay. So once you know carbon monoxide and hydrogen gas, you're plugging those values into each of those concentrations. Don't forget to square that one. And how did you solve for X? Like, how did you rearrange this? Did what with the math? Come on, people. Multiply the denominator over here, solve for X. And then that should be that number. Yeah. Nothing. The K expression is, the expression is still the same. Like, that's the K expression. That's the substitution of those variables. And the Q expression is the same. It's just when you're plugging into the Q expression, you're plugging in initial concentrations. when you're plugging into the K expression, you're plugging in equilibrium concentration. So the setup's the same, it's just the numbers are different. Okay? Okay, so then 2, you have, I'm going to go all the way down. Okay, so you have only HBr given to you, and it said that equilibrium bromine was determined to be 0.13 molar, what's the value of Kc. So you're given this initially, and then you're given a Br, but Br, bromine, not gas probably, it's probably liquid, but no, we'll call it gas because then liquid would be not part of our equilibrium expression. We're going to call it gas. Given the fact that you make this in a 1-to-1 ratio with H2, then you were also able to figure out immediately the other product. And since you're producing Br2 in a 1-to-2 ratio with HBr, you're subtracting twice as much of that same value from the HBr to give you an equilibrium condition 0.5 minus 2 times 0.130 to give you 0.24 molar. Give me a thumbs up if you were able to get here. Okay, so just, write down what you need to. But the idea is that if they give you one of the conditions at equilibrium, you can easily find the others by looking at the ratios in which they react. And then from here, setting up the expression, plugging in the equilibrium values, that would be giving you then the Kc value, which is going to be 0.293. Okay? Give me a check or something, I can move on. Okay. All right, so turn and talk to the person next to you on 3 first, and then I'll answer questions 2, which is more of a challenging one first.
Well, I understand.
All right, so come back to me on 3. Sorry, I know some of you guys are ahead of others, but I'm trying to make sure everyone's on the same page here. Okay, listen up. Give me a quick thumbs up. You got your initials. Okay, we started this one yesterday in class. So you got your 2 liters. You did have to divide by the liters to get the molarity. They gave you K. Yeah, so they gave you K, and they said find the equilibrium concentrations of all those stuff. So you don't know anything else about equilibrium, so you have to use X's here. You can't use true numbers. Since you had a reactant concentration, you must be subtracting from reactants and adding to products because that's the only way you can proceed. So you subtract X, add X, and these are all in a 1-to-1 ratio, so it's quite easy to see that. So once you take your concentration minus X, X, and X, what are you doing with these equilibrium values? Plugging them into the expression. So the expression, which products are reactants, right? You get X times X over 1.5 minus X times 1.5 minus X, or 0.15 minus X. Simplification of that, X squared over that squared. That is now a perfect square. So if you square root this and the value of K, it makes your math so much easier because you don't have to deal with squares anymore. So once you get there, and this is kind of where we got to yesterday in class, taking the square root of 0.5 is 0.707. Square root of that is just a single of each of the reactants, or the numerator and denominator. So then to combine like terms and solve for X, you have to do kind of a series of algebra steps. But this right here, you cannot just pull out the 0.5. 1 second. You cannot just pull that out. You need to multiply it by the whole thing, this whole, what do you call this, function, multiplied by the 0.707. So 0.15 times 0.707 is this, and then 0.707 times the negative X is that, equals X. So then when you add 0.707 X to both to negate the negative, You add it to the other side. This is a 1x, so 1 plus 0.707 is 1.707x is equal to that same number. And then when you divide by the coefficient in front of x, you should isolate x to be 0.062 molar. Question, JT? You'd have to set up probably till about here. Yeah, you probably have to set up till about here, and then you could plug into the solver. Just be clear, like at the end, you solve for molarity, and this is not the final answer. The question was asking about equilibrium concentrations. So you had to plug these x's back in here and here and here and here. So then these are your final answers. They're kind of cockeyed, but they're here. The two products are x, so they are 0.062 molar. The others are going to be subtracting that x, so they were 0.088 molar. Now, this is something that you should be getting more comfortable with. It's just making sure you remember, like, your algebra. Okay? I know it's a little bit of a stretch. Question? If the math is more challenging, we're going to get to that today. The math is more challenging, like you got to use quadratic, or you got to use some crazy higher level, higher than that cube. It's not cube. What's the one for cube? Just cube? Quadratic has its own name. Cubic equation, function. Okay. Like if you got to go to that level, then you're probably going to be neglecting x. We'll have some other key signs for that in a second too. Okay. All right. 4. This is the one where you had a series of reactants and product concentrations given to you. So you're given 1 molar for all the reactants and products. Since you're given all quantities, you do not know which way to proceed, left or right. So you have to find what first? Q. You have to find Q. So when you plug these data points into the expression, which is products or reactants, these all matter. When you plug in, oh, sorry, it wasn't 1 molar. It was 1 mole per 100 liters, which is 0.01 molar. So that's 0.01 molar squared over 0.01 molar squared. So Q is equal to 1. How does that compare to K for this particular one? It's bigger. So does Q represent too many products or too many reactants? Okay, if Q is high, that means numerator is too large. So too many what? Products. So I need to get rid of products, which means proceed left, right? So away from products. So that's why I'm subtracting from the 2 products, adding to the 2 reactants. So then I get a series of numbers plus or minus x. These are the values you plug into the equilibrium expression for K. So we're going to then set those equal to K. A lot of times, this is going to be very common. A lot of times you'll have a perfect square root. So you'll have your products or reactants, and you'll notice that these are the same, so these are both squared. So then we're going to square root the entire expression equation. And then, 1 second, Darcy. And then square root of 0.4 is this number. You're then going to have to combine some like terms to get x by itself. So it takes a hot minute, but when you multiply the denominator, you just pull your x's over, set it equal to the numerator 0.01 minus x. Then you add this x from here over here, and then you subtract the number to combine the numbers. You should get 1.63 x is equal to 3.675 times 10 to the negative third divided by the other number, solve for x. 2.25 times 10 to the negative third molar. Question?
So, in the question, it doesn't ask you whether it goes like left or right. So do we just automatically assume that one of the question has like all the molarities of images that we have to mention?
Or you have to utilize that to continue, yes. So if they're ever giving you all of them, you don't know which way to proceed. So you have to figure out by comparison Q and K.
But like, I didn't do the Q at all, but I ended up with the same answer.
So you may not get credit for the first point of solving. So did you subtract from reactants or subtract from products?
Reactants.
How'd you get the same answer then? Because I mean, it's so these numbers are, I mean, these value setups are so close, a plus and a minus. So I wonder if someplace you switch to plus or minus. But I could look at that in a second. Questions on setup here? Yeah. That's why. Okay. So if it was you can't have a negative concentration, right? We can't have negative matter. So the idea is that you got the numerical value right because of this nature of how these are so similar. So in the end, you would have known that you would have gone the wrong direction. But yes, you should do Q versus K first. Okay. So at this point, you're finding concentrations. by plugging in the X value you found. So the concentrations of, what was this first one? Oh, this was the 0.01 plus X, so then we ended up with essentially the same values. Oh no, sorry, not quite. 0.02 or 0.0123, and the other ones were subtracting X, so then you get a smaller value. Alright, so are we doing okay? Okay. I did not copy 5 here. I'll go pull back up 5 in a second. I'm going to jump to 7. These are the ones that specifically I want to make sure you're clear on. But 7 is a weird one because you were given a value of Kc to be 9.40 for the value of Kc. But when you saw your reaction, it gave you sulfur solid, and carbon disulfide gas. None of these matter except for which one? Right, so just this carbon disulfide. So essentially your Kc equals just the concentration of carbon disulfide. They kind of threw you off by giving your 10 molar first, but it doesn't matter. I kind of like initially just like, yeah, icebox, but it doesn't matter once you kind of get down to the nitty gritty. So Kc equals the concentration of that lone product. So therefore the number is equal to the molarity of Kc, or carbon disulfide. So that's the information that you now know. But the question asked to solve for moles. So they told you initially it was like a 5-liter container. So molarity times liters will always give you moles. So you kind of had to see through that question before you were working too hard. You started working too hard. Okay, I figured most of us probably would there, but then after that, you should clarify and how to simplify. Thumbs up, can I move on? Yeah.
I understand that, but I just don't get how you like go from if they're all like molar for like on the table.
So the significance of being in molarity means that we're solving that we can plug those molarities into the Kc expression. But the way this particular one works, we never express a unit on K, so like K is just a number, but with respect to how this one worked out, the concentration is equal to this numerical number. So essentially, I'm just saying this is the concentration, so I had to add a molarity back to express a value as a concentration. So you're right, Kc is not 9.4 molar, Kc is just 9.4. But when we express it as concentration, it had to have a numeric or a unit as well. Did I answer your question? Kind of. Ask me again later. Okay, so the next one, 8. I misnumbered it. There weren't 10 questions. You guys probably saw that there were 9. But in 8, it told you Kp. Oh, and these are, I fixed these on my actual paper, but here it is. They told you Kp was 0.25, and you only had 2 gases, carbon dioxide and water. So given that Kp is 0.25, the partial pressures of the 2 products there that are gaseous are in a 1-to-1 ratio. So if you plug in x and x there, you get x and x is equal to x squared. So then just to solve for 1x, you're going to do what? Square root, right? The whole thing. And then you get x is equal to 0.5. And since we are talking about partial pressures, we're not going to put molarity there. We're going to put a unit of pressure, which will be atmospheres in this case. Yeah.
Just making sure, do we want to avoid putting over 1 because I did that?
Just avoid it for now. I have a friend who's a grader, and she's like, they don't count that right because then you think that the concentration of this matters, but it doesn't. So I've stopped putting things over 1. On my keys, I've tried to like you can see the big white space because I whited that out. So I've tried to stop doing that as well. But they like to randomly throw in their own rules on grading, so I try to make sure we're clear. Yeah.
Did it mention atmospheres or did you just
No, just assume atmospheres for all partial pressures unless otherwise indicated, but they would give you credit no matter what because it's just a unit of pressure. Yeah.
Is it indicated what unit they want in the pressure, or that means the answer would automatically be in that unit, or the unit would change?
I don't think the answer would automatically be in that unit. Yeah. Okay, so the last one, which was 10 on your paper, but it's actually 9, you had 2 gases, kind of the same story as number 8, but the idea was that you had Kc given to you, noting that we're talking about pressures, you had to then convert Kc to what? Kp first. So Kc was 1.8 times, or 1.81 times 10 to the negative 4th, plugging into the RT to the delta N. How did I get 2 for the delta N? right? So I did 2 moles of gaseous products minus 0 moles of gaseous reactants. So that's how you get 2 there. So Kp is equal to 0.1083. So that Kp value is well used to then identify the partial pressures of each of the 2 gases that were in the products. So this is the Kc or Kp expression. It's just a matter of concentration versus partial pressure. And then once you solve for Kp, plug it in here. These were made in a 1-to-1 mole ratio, so it's an x and x. X squared, how do I solve for x? Thank you, square root the whole thing. And you should get the partial pressure as 0.329 atmospheres. Or then the secondary question, which is you'll see this quite often, like know this, as you get partial pressures, it'll then ask for the total pressure at equilibrium. Do not multiply those. Think of partial pressure with Dalton's law. To get total pressure, we always have to do what? Just simply add them up, right? So that's a very common question given pressures. So like this is a good free response question, something like that. Okay. And then other questions right now. Yeah.
When do you do the inverse?
If they ever flip the reaction on you, the reverse reaction, you invert the K. Other questions right now? Yeah.
So, but with that, did you solve for two anytime that was still inverse?
No, don't flip a reaction yourself. Like, don't, if they give you a standard reaction and you're finding Q and K, just make your icebox and then subtract from products, add to reactants. Yeah, so just kind of read from right to left, but do not flip the reaction. Okay, they'll have flipped the reaction for you, like, hey, what's the K value? You've had one reaction, they give you a flipped version, then they ask for you to solve for K. All right, I didn't go over a couple. Do I need to go over 5? Yeah, okay. Oh yeah, this was the one I was waiting on because it's a neglecting X. So I was holding off on this, but I am going to teach you guys the neglecting X in more detail. So pay attention here just a little bit, and then I'll just have more neglecting X we need to do. So they gave you molarity of HCl, and then noting there were nothing for the 2 products. They told you the K value at a certain temperature. You had to solve for the equilibrium concentrations, I think, here, right? So you're subtracting a certain amount from reactants, you're adding to products, so minus 2x plus x plus x. Who set up the ice table correctly? Okay, so you're just plugging in numbers and x's, okay. And then your expression, which is products or reactants, you have 1 product times 1 product, so in this case they were both x and x, so I just made that x squared. And then over reactant, so that's concentration of HCl squared, so that's concentration of HCl squared. But since we have a net minus 2x here, this is going to start looking quadratic, and we're setting this equal to K value given. So the moment I see this, a little scared, thinking quadratic, but then I notice it's a what? Perfect square. So then I can square root the whole thing and then simplify. So x over 2 minus 2x is equal to the square root of the K value. Takes a minute to isolate x, takes a minute to solve. But you can see here, I showed all my math, so it's very clear, like mathematically, how we're isolating x. This method, I got x to be 3.578 times 10 to the negative 17th molar. Not made a good role model, there's our units there. So that's a little bit challenging. But then, as we spoke of yesterday, how do you know when you can neglect x? The value of this K value is high or low? Super small, right? Does this reaction really proceed to products? Probably not. It's a favoring the reactants quite a bit. So are these x values going to be large? No. Like, it's not going to subtract any reactants. It's not going to make barely any products. It's a very negligible value. So to very much simplify the math up front, you can do the neglecting x thing, which is where we did the /0. So you can still get x squared over 2.0, but x squared over 2.0 squared, sorry. When you then multiply that by the x value, the K value, you can just square root that, and you get x to be 3.6 times 10 to the negative 17th. Look how close that is, though. Right? It's super duper close. Now, I would then need to show the 5% rule to make sure it's legit. Like, I can assume that's negligible, but it's teeny, teeny, tiny. I know that 10 to the negative 17th is going to be way less than 5% of what number? What number would I have subtracted it from? What number? 2. 2 is the only number I'm manipulating x from. So I know that 10 to negative 17 is way less than 5% of 2, so I didn't run my 5% rule, but you should. Questions there? William?
So why would you do all of that and then just you did all that first part of your equation and you said, well, this is really small and you go ahead and pick up the exact answers?
I did that for for the teaching moment. I would not do that on my own.
Okay.
I probably would have been like, hey man, this K is pretty daggone small. I'm gonna neglect up front, double check. Yes, it's neglectable, moving on. But I wanted to show you could do it. You would be right in both methods.
Okay, so like upfront essay, et cetera, 3 times, 2 times.
Yeah, I'm like, holy cow, that's small. I'm probably not gonna make very many products. Okay, so yeah, that's just for the showing you that you could get it right both ways. Okay, all right, let's take a stretch break real fast. Get up and talk to somebody about, equilibrium or life. What you're doing for the holidays, what Santa's bringing you, if you believe in Santa.
I'm ready for committed to college that first day.
What? Hunt. Hey,
It was $200.
oh, did I not? Oh, I didn't see this today. Put your name on the box for me. Thanks. Oh, because I'll have to write it down and put it in the grade book.
It's called like 90 Americans that changed. No, but it's they're not bad either, but I don't want it to I'm just trying to get my nose. I'm not even thinking about it. I found it. Actually, I had my mom send it to me because but I have them, and all the questions that I had, it was left and right. The questions where it has the math sign on it, I didn't square root it before, so I tried to solve it quadratically, and it went really bad. Yeah.
So this is 1, 2, 3,
4. That's 10.
10.
And that's 5.
Okay, you're good. Thanks, darling.
You're welcome.
Hey.
I'm basically done. No, first semester's over.
You can't have 0
That's crazy.
All right, come back to me. Come back to me. Let's go.
And our break was the first week of last year, they're making our tests or midterm or whatever, like during school, so
All right, we're going to talk through some of these and we're going to solve some of these, okay? Stand up if you need to, yeah. Gosh, some sleep, people. Oh, I just watched this TED. Does anyone else subscribe to TED?
I love it.
Okay, so they just sent this other one, this video out last night. It was like the benefits of, or no, like your brain on deep sleep, like, like your brain on drugs. Deep sleep works a whole lot better. So, when do you really, like, need deep sleep in your REM cycle?
Stage 4.
Okay, stage 3 or 4. Who needs REM? Who actually hits that deep sleep?
Not really.
I think it's like probably like 3 or 4 hours in, and then it's 5. But there's a cycle. Like you have the cycle. Okay. Alright, so you should be getting between 5 and 8 to give your body the opportunity to meet that deep sleep cycle. Okay. Sorry to distract you. Come back to me. Okay. So look at this question and tell the person next to you how you would solve it, but please take a minute to read it. We're not going to solve this one. I want you to know that you could.
Oh, we're not. I just saw this. All right, come back to me.
right, Carrington and Andrew, tell me how to solve this.
Since it's given that it's already in an equilibrium mixture, you can just plug that into your K equation, which is the concentration of
That times that over that times that. Okay.
and then you plug in the concentrations in,
And then what would you be solving for?
you would solve for ethanol.
And ethanol is where at here, guys?
You would C2.
Okay, so this is ethanol. So that's going to be a denominator. So you have number times number over number times x equals number.
You would multiply
And then
by number x.
multiply over here
By number.
and then divide by number to isolate x. Yes.
Yeah, but like, water's a gas, so does that not matter?
It does matter. It's a vapor. So we're going to use it in the concentration.
It's not eight.
Well, we would be giving we're giving concentrations for all these. So you can still have the concentration of a gas. It's maybe not molarity, but it's still concentration of a gas. Or it's maybe dissolved. It might be dissolved in a liquid suspension. So you can have like water bubbles, vapor bubbles in the liquid solution. We're going to go with it being gas, and then this is the concentration we're using. Okay. If they tell you state of matter and it's an important state of matter, then you must use it. Okay. All right. Next one. Solve. Read and solve. Try to read this by yourself and solve by yourself first to see where you are. And if you can ask me where that's going. Start by yourself, guys. You get the information on the board you need? Okay. I'm just don't look up here yet. Don't do it. I lost my place, so I can't keep going. How are we doing, guys?
I was great.
On a scale of 1 to 10, do you understand your process? That's not on scale. Okay, okay. So, let me tell you what I expect from you. I expect that you're, like, especially if your response work, right, where I can give points and can't give points for some things, I'm expecting that you're setting up an ice table of sorts, right? And even if you don't want to write the whole, like, 3-layered work, you could at least write in the top up here, 0.2 minus x, 0.2 minus x equals of 2x. Like, but keep writing out ice because you're not that good yet. Okay, let's be clear. You're not that good. Use ice. Setting up your expression is important. Many times that is a piece of the FAQ, like part B, write the expression. Part C, solve for equilibrium concentration. So you do need to plug in, like we have here, equal to the K value. But once you get to the math, I mean, I wrote down every step just so you were, you know, I'm helping you review that 8th grade math. But I know that you don't have to write all those steps down for yourself. You can rearrange and you can solve for a lot of these very quickly in your calculator. But what I'm expecting is that you're at least here and maybe here, like you've simplified it by square rooting both sides. But all this junk down here, show me a little bit of it just so I can like catch a mistake if I need to catch a mistake. But there's no like points given to you in here. It's like setup, simplify, and then final answer of x. But then that's not really the answer. It's concentrations is what I was looking for. So once, did you guys get x by the way? Sorry, I'll take questions in a second. Point. So, and I stretched it out because I'm not to my final answer yet. There were 3 sig figs up here in the very beginning of this problem. So HI was equal to 2x at equilibrium. Multiply that by 2, you get 0.312 molar. Check. And then concentrations of H2 equals concentration of I2. So you can kind of make that easy by simply setting them equal. Subtracting x from that should give you 0.0443 molar. Question? Mm-hmm.
When we created your response before, it's been like really picky about certain steps. Do we need to include the like the 0.2 moles over 1 liter produced? Can you include that now?
No, you're good. You can go straight to that. The only time that would be really picky is like if it asks for like how many moles are present here, like in our one of the kinetics ones we just had. Okay. All right. So is it the red stuff you're still practicing a little bit? This math. Some of us have a better memory than others, so that's going to be a kind of hit or miss. Now I'm going to try to tell you how to use this user solver or pull your calculator. Okay. Now I have a TI-99 and I can't remember how to use it exactly in here. So if you go to like math. Go to math and go to 0. So solver. Oh, sorry. So B. Well, some of us have different numbers than that. But you go to math and then you go to solver. You hit equal or you hit enter, and you have an equation editor. Essentially, you have to either, like on many of our calculators, I think you can enter JT on yours. Can you enter like this in?
2x.
Can you enter like this whole function into the equation 1, equation 2?
Or you can put one of them, like the 2x and the E1 on the other side.
Yeah. So who has the E1, E2 equation set up? Who has just like 0 equals? That's what I'm more familiar with. So if you have a 0 equals, you want to set the equation equal to 0. So all you would do is you could get to this step here in your own personal math, and you could just subtract 2x. So you could literally plug in, if you're of the 0 one, put in 7.0356 parentheses 0.20 minus x parentheses minus 2x, and that essentially has been set equal to 0. So at that point, you have to guess a number. You literally just guess 1. 1 second, Darcy. So if you put parentheses minus 2x, I'm looking Miriam. So if you hit enter after that, it's going to ask for you to guess x. You do have to, when you put 1 in for x, you have to hit alpha enter because you need to get the solve feature. And there's your answer. 0.155. Thanks. I don't know. Use I plug in 1. If you plug in 1 and then you hit alpha enter, it'll solve for us.
Just do alpha
You can't, there's no other way to do it. You can't just like solve it out by
Okay, so the only way you'd use this in here is if you got to the point where you could map and you're like, oh my gosh, I don't have time to map. Here's my guess right now. And as long as you put your calculator correct, you're good. If you've got Butterfingers, you need to double check that twice because then, you know, you have no mathematical support to figure out if you made a mistake or not because it's all in the calculator. Okay? All right, moving on. Let's go to neglecting X problems. I think I've got one or two of those I want to do now. Hold on, let me see if I want to do this one. No, you guys can do that one. Yeah, I'm good. Okay, so very quickly, please read why in the heck we would neglect X. This is going to be like the key signs when you would neglect X. So take a minute and read that. This is stuff we did speak of yesterday and today a little bit, but if you were clear. Right, give me a thumbs up when you've written down what you need to. So essentially, if the math gets hard, probably going to be neglecting X. Especially if you're producing products where the K value is very small, it means that it's very, very favorable in the forward direction. So therefore it does, in the reverse direction, so therefore it does not want to go forward, it does not want to produce very much product. And then we have to show the 5% rule justification at the end to say, yes, I'm clear, like this X is negligible enough to make no statistical difference. Yeah.
So could you neglect X if the K value is really, really, really big?
Only, and I have one example with that, only if we are moving in the reverse direction. Like I start with products, and they want to be there, like that's the K value saying I need these products because I have a large K value. So if you're subtracting from products and adding to reactants, then it may work out for us that way. I have one we're going to walk through with that one. Okay, so let's go through another sample of this. I do have these printed on the prop. It says like neglecting X problem set, or it just says neglecting X. There's only 4 problems. It's on the upper left-hand side of like the second page. Okie. All right, so work with me here. We're gonna do this one first. I added 2 states of matter in here. On your paper, it may not be there, but you can write down the phrase within the board. For the following equilibrium, for the following equilibrium, 1.00 times 10 to the negative 13. That's the equilibrium constant. It says the equilibrium constant right here. If the initial concentrations of iodate and H plus are 0.002 and 0.065 molar respectively, what is the equilibrium concentration of iodate? So initially they give us values, right? So what do we have set up? Ice table. So they didn't give us initial values for everything, so we're not doing what first? Q versus K, right? So if they did give it to us for everything, we would be running Q versus K. All right, so we're given 0.002 molar for who? Iodate, okay. And we're given another concentration for hydrogen ion, so 0.065 molar. Are we given anything for this? No. Okay. Why am I excluding liquid and solid? Because it doesn't affect the equilibrium. I'm going to exclude them from the icebox as well. So you can even put like a slash through those just so they're not distracting. And then well, we also know the K value. Sorry, my grammar's messed up, but that's the K value. Go ahead and what am I plugging into C? Yeah, there's 7 right coefficients here, minusing 7x here, and then what here? Another 7x in here, plus 5x, because there's a 5, a 7, and a 7. Okay, so don't be scared, just big coefficients. So then we get 0.002 minus 7x, 0.065 minus 7x, and then just 5x. So this is our equilibrium condition. So what do I do with these? Plug them into my what? The K expression. So I have not written the K expression out yet, and I do need you guys to write that. So I'm ready when you are. Okay, C equals. I'm not going to plug variables in yet. Can we write the full expression out first? H, concentration of H5 iodate. Nope, IO6. That's a 1 minus charge. Okay, so that's raised to the 5th power over iodate to the 7th times hydrogen ion to the 7th. Okay, well now what am I plugging in for these? 5x to the 5th. If you don't write this first, very commonly people forget the exponent, so that's why I always make your expression first. So then that's going to be ringing a bell. And then 0.002 minus 7x to the 7th, and then 0.065 minus 7x to the 7th. Holy moly, this is crazy, right? So now I gotta set this equal to what? 1.00 times 10 to the negative 13. Okay, so the moment I'm seeing all these 7th cubic equations, 7th-ish equations, I know that I'm not going to be running the math, especially since I see the K value is what? Very small. So essentially that means are there a lot of reactants reacting? No. Are there a lot of products being made? No. So the X value is going to be hopefully negligible, but you know we're going to just trust our gut with this. What am I neglecting? The 7x and the 7x. I cannot neglect this x because I need a value to solve for. Plus, it's not being added or subtracted from anything, so the math won't be that bad. So simplify. What do I have? What's 5 to the 5th? 5 to the 5th. 3, 1, 2, 5. X. What? To the 5th. Thank you. So I just fifth of that one. And then this value to the 7th, this value to the 7th. I need a denominator when you guys are ready. Ready when you are? Times 10 to the negative 28th, very good. Equals 1.00 times 10 to the negative 13th. Now go ahead, rearrange in your calculator, solve for x. If you want to plug in the solver, you can, but this is not that bad to mathematically solve. Compare to the person next to you to make sure you plug in your calculator right. You don't necessarily have to do 5th root. You can raise it to the 1/5 power. 1/5 power is the same as 5th root. Alright, check with me on the board. 1.822 times 10 to the negative 9. Alright, so we neglected x. What do we have to do to back up our process? We have to show the 5% rule, right? So, and I just noted here we would have this as 2 sig figs because we would be plugging these back in. So who remembers from yesterday how to support our work with the 5% rule? Say again? So tell me what I'm doing with the lowest value though. Okay, so you take x, So x divided by the lowest value you would have added or subtracted it from, which was what? Okay, so 0.0020, and times it by 100, and we're going to figure out what that percent is. So x is that divided by, what's your percentage? Small. It's small. It's 0.000091%. Yes, it's less than 5%. So I want to see you write in you don't have to title it, hey, here's my support 5% rule, but I need to see this, where you plugged in the x divided by the lowest value you would have added or subtracted x from, and then the percentage. And you don't have to put a happy face, but it would make me happy if you put a happy face, just to verify that you have now checked that you're neglecting x as possible. Yeah. Yes. Times 100. That's right. 9.1 times 10 to the negative. This might be hard to see. There are 4 zeros there. Yeah, you're good. Okay, thumbs up. Yeah, question?
So instead of putting like x over 0.002, we put 0.002 to 0.05 and compare it.
You can. It's just not the conventional way of showing that. It's just that's just how they would normally show it, but it works the same way. All right, let's talk about the second one. I got about 15 minutes here. Okay. So read the setup here. Get your stuff set up first, and then we'll solve together. I need to walk you through this. I mean, you're good to be. I think you're thinking critically, which is good. I just don't know what you're thinking about right now. All right, have you guys set up your ice? Oops. So what did you guys set up here? What did you set up for methane? 0, because it doesn't give you any conditions for methane. What does it give you for ethane? 0.52 molar. And hydrogen, 0.06 molar, and it also gives you what? This is the Kc value, 9.5 times 10 to the negative 13. All right, before we move on, I want you to see if there's I want to see if you're thinking, what does this mean right now? All right, reactants are highly favored. How do you know that? Okay, very small, okay? So, reactants are very favored. What do we have set up here, though? We have no reactants. Okay, we have a lot of products. It doesn't mean products are favored. It's just like, hey, I threw in products first. What do those products want to do? Like, they need to get wiped out, right? They need to be gone, essentially, because you need all those products to form reactants. But what we're going to do, and I'm going to show you this, and you can write down parts of this if you wish, but here's our problem. This is not matching this. It's opposite of what it should look like. So what we're probably thinking first is like, oh, icebox, right? So we'll subtract x here, add 2x here. So then we would have 2x, 0.5. I don't know why I keep wanting to 0. Just a thing now. Okay. Minus x, 0.52 minus x, and then 0.060 minus x. Because we have to pull from the products to make the reactants because we don't have any reactants. So we'd probably set this up first. And then we would go, okay, Kc is equal to 9.5 times 10 to the negative 13 is equal to what? 0.52 minus x, 0.06 minus x over 2x squared. Good, because we're doing that to the second power. So, what would you, noting that this is a very small value, what would you probably then think to do? Neglect x and solve. Can you guys solve for x real fast for me? I mean, not in your head. Calculator, please. Neglect X and solve. Let's see what this is. Compare your X to the person next to you. Yeah. No, you only neglect X's that are added or subtracted. So we're only able, we are going to neglect X. We're only neglecting this X and this X. Because if you neglect this X, then we have no X to solve for. Alright, what do we get, guys? 9, 0.
6, 1.
Holy moly! Look at the size of that X, right? Okay, so were we able to neglect X? Yes or no? Okay, okay, you guys said we neglected X, whose value is very small. Are we able to neglect X with given this value? Is this 5% or less than the value we would have added or subtracted from? No, okay, I got through. Anybody else on board with me? Okay, we got to be in the same ship or I'm not leaving the port. This could not be neglected, yes? Okay, so that means that this problem, we were right to be a little cautious at first to be like, okay, well, products are all here, but reactants are highly favored. So what we have to do first in this problem, this style like this, and we don't see this incredibly often, but I just want to make sure you're aware of it. We have to let this reaction run to completion first, and then let it get to equilibrium. So we're going to let it react in the reverse direction, and then we're going to bring it to equilibrium. So write this reaction again. Okay, so not going to neglect X, solve a different way. That's basically what we're doing. So, what was it? 2 methanes equilibrate to ethane and H2? Yeah. Okay, so it was initially 0, it was 0.52, and it was 0.060 molar, right? All right, so we're going to let this run to completion by figuring out who's going to control the reaction in the reverse direction, aka LR. Who's the LR?
Emma,
Yes?
at 8:30, could you send Margaret Lamars to the attendance office for dismissal?
Thank you. Yeah,
Thank you.
okay. So, who's the LR here? Come on, guys. Hydrogen. Okay, so LR, subtract LR. Subtract LR in the same 1-to-1 ratio, because that's how this stoichiometry works. Subtract LR in a what ratio here? 2-to-1, right? So 2 times 0.060. I'm sorry. That's an addition sign, guys. Okay. So subtract, add. We're letting this run to completion first. So we have 0 of this. We have what? 0.46 molar. I think it's 266. And then we have made 0.012 molar. Yes, yes? Is that math right? Yeah? Okay. So now we have allowed it to run to completion. This is looking better for, yeah. Huh? Oh, yeah, it is 0.12. So, yeah, please don't be afraid to correct me. I'm rolling through this in 5 minutes. Here we go. So we have now conditions that look a little bit better for starting our equilibrium process. Because our K value is still very small. We have no products. That makes more sense, right? Because there's no favorability of products at all, and we have more reactants. So now let's ice it. Okay, so from these conditions initial, now let's ice it. Okay, so what am I doing in ice? What am I changing? So I'm subtracting what, guys? Subtracting reactants or products? There are no products. I cannot subtract from nothing. No products. So I have to subtract from reactants, right? So I have to proceed from in the forward direction now. I proceeded in the reverse direction just so I can run it to completion. that's because I need to make some reactants first. Now the reactants are going to come to equilibrium by subtracting 2x, because that's the 2 for methane, adding 1x because we had 1 ethane, adding 1x because we had 1 hydrogen. So then now at equilibrium we have 0.12 minus x, 0.46. Thank you. And then 0.46 plus x, and then x. So these values I'm going to do what with? So plug into K. Now, K was what was it? Was it to the -13th? Was that this one? Oh, that was the other one. Okay. 9.5 times 10 to the -13th is equal to products of reactants still. So here's our product. It was just there's one of those. There's one of these products. So that's 0.46 plus x. And there were 2 reactants, so we have this raised to the what power? Squared, right? So the second power. Okay. I'm still seeing what equation come to life here if I have to solve. I see squared, right? So I start to see quadratic, right? So I'm probably not going to be using quadratic. So now I can still use my same logic. K is small. We don't want a lot of products to form. We don't want a lot of reactants to react. So what are we going to do with x? Okay, which ones are we neglecting? The bottom one and the 0.46 one. Not this one, because then I'll never have an x to solve for. Okay? Now, neglecting those, solve for x. I'm just going to write some simplification real quick. There's no rule for that. It's only the ones you are adding or subtracting x. I'm adding or subtracting x from this, and I'm adding or subtracting x from this, but I'm not doing it to this x, so I'm not neglecting this x. Right, 1 second, Cassie. So, give me a thumbs up if you solve for x, and it's approximately here. Yes, yes? Okay, so here, now let's go back. Does this make sense for our problem? Yes or no? Okay, we said reactants are highly favored. Not very many reactants react. This is true. Not very many are reacting. But then we're going to do our proof with what? What's the how do I do this 5% rule? So x divided by, so between these two values, 0.12 is the smaller one. So what is that when you get your 5% rule? 2.47 times 10 to the -11%. So, yep, we were able to neglect that because it's less than 5%. Cassie?
Why did you do the first answer now? The first answer?
Yes. So, I'm going to walk back through this, okay? So, we went, was this the question? Okay. So, naturally, we would go to ice table here. That's just our natural next step. When we go through the ice table and we see that the K value is very small, but we have a lot of products, that should kind of ring a horrible bell. Like this can't be the place where I should be because I have too many products for such a small K value. But we ran through the K setup anyway. We set up by ice, we plugged our values in. We saw for x, x was huge. If x is huge, and 1, that offsets our 5% rule 100%. Like, we cannot neglect this x. This was incorrect. And plus, it was huge, which meant that I was subtracting a whole lot of products and making a whole lot of reactants. But therefore, I would have to run through the math again using quadratic. So, since we're using quadratic, we're probably not going to be, we're not in the right place. So simply by the nature of comparing KC is small and having all products, I went ahead and assumed that this reaction would have to go to completion before I could find equilibrium. That's kind of the key sign you'll see here. If it's not agreeing with the KC value, then you only a completion reaction first. Yes.
So that's how you automatically, like, the way to know you're gonna do the equation is you're automatically matching
I would say, yes, that's a pretty good rule of thumb, but especially even after running through ice, and you think, oh man, I can't neglect, this is a huge value. It's very, very, very wrong. Then that's going to trigger me to also consider the other route, which would be run to completion first. Yes, unless it's a like a limiting reagent problem, like non-equilibrium.
It says
That would be a non-equilibrium problem. Like that would be normal story. Yeah. Question.
So if we see this situation where you supposed to be accomplished at the first,
if you run it through your calculator and you realize it's not going to work, like you're probably not getting points for this, but it's a nice way for me to show you my thinking process. So you can run it through your calculator to see if it works first. Okay, let me stop on this one. This one, like I said, this was a challenging one, but you will not see this very often. The one we would see would be like we have here. If you were good with number one, are you okay with number one? Were you okay with this other one that we did with the this one? Yes? Okay. Just calling probably for you. So let's do this. We're going to go, oh, they didn't call. They hung up on me. Let's go do one more thought. We leave in 4 or 5 minutes, so please don't back up yet. Don't be disrespectful. When do you solve for just x? Just a thought. When can you solve for just x? When will you not see the quadratic equation? When you don't have, okay, how do I get rid of squares? A perfect square root, right? Okay. Okay, if you had to use a quadratic equation, it's because what did not get met at the very end of all your process? Okay, so normally we neglect x because we're starting to use the quadratic, right? But what if x is not negligible? Well, maybe not that you did it wrong. If x is not negligible, it's just not small enough to neglect. So you're going to have to do the math. You're going to have to use a quadratic equation. But instead of solving for quadratic, I've shown you now how to make that easy by using the solver in your calculator. If you want to use quadratic and do negative b, like you can go do that. But I'm still telling you to use your solver too. Okay, how do you know that when you're done, you are able to stay with your neglecting of x? You have met the 5% rule, which is x over the smallest value you would have, added or subtracted from. And then, how do you know you need to go to completion first? All right, so k value. Okay, so k value can be huge, and who do you have more of in the initial setting? Reactants, which that is a mismatch, or k value is really small, and you have a lot of k value is really small, and you have a lot of products because there's a mismatch there. Basically, k does not match the initial conditions. That's one way of thinking about it. Yeah, all right, that's good. And then this is homework, okay? So I actually thought we'd get to some of this in class, but I think I spent a lot of time going over some things. So let's do this. I do want you to go through the textbook problems, which are those 1, 2, 3, 4 listed there. If you feel good about just calculating k from equilibrium or solving for equilibrium concentrations, I don't have the quiz made yet, so I'll probably be a nice person and just maybe not do neglecting x, but it's going to be short and sweet. It's not going to take more than like 5 minutes. If you guys can complete the exercises, and you know what I'm talking about, the exercises and the reading, you don't have to do it by tomorrow, but by, tomorrow's Thursday, by Friday, that'd be great, okay? But we are going to be talking about that homework tomorrow, okay? So 4 comments from textbook, and then a quiz. If you feel good about the problem, like now that you do the problem set, and you want to go back to some of those are some things that we're going to be expecting to do. Okay? I gotta make this quiz. For the question.